talking about time setting in overcurrent relays. This is our overcurrent relay, which is being fed from the CT secondary. So it is having a current input, which is coming from the secondary of the CT, and its output is the trip contacts. So these terminals are connected to the trip circuit. It is having two settings, pickup setting and time setting. Pickup setting or current setting of the overcurrent relay has been discussed at length in my past video, in my previous video. So in this lecture, I will try to focus on time setting of the overcurrent relay. So time setting feature of the overcurrent relay helps us to adjust the operating time of the relay. So in the lecture overcurrent relay basics, I have already defined what is meant by operating time of the relay. So this can be adjusted by using the time setting feature available in the overcurrent relays. But here something appears contradictory. So we all know that fault should be cleared as quickly as possible. The faulty section should be isolated as quickly as possible. In the sense, relay has to take less time to detect the fault and to send information to the trip circuit. If relay has to take minimum time to sense the fault or to close the trip contacts, then why to adjust the time? Why to increase or decrease the time setting? The first question comes is, the first thing is that why this feature is necessary. Second aspect is that how time setting can be done. So first let us address this, how time setting is done. Then later I will try to explain why it is necessary. To understand how time setting is done in overcurrent relays, we need to have a picture of the internal construction of an electromagnetic overcurrent relay. Although I have not yet started construction of electromagnetic overcurrent relay, I'm trying to show you what happens inside an electromagnetic overcurrent relay. So this is an aluminum disc, and this is the spindle of the disc. So this disc is placed in the influence of magnetic field created by the relay coil. So the relay coil is being fed from the CT secondary, and it is producing a flux, and that flux will be responsible to produce operating torque on the disc. So operating torque of the disc will try to rotate the disc in this direction, whereas the spring which is mounted on the spindle of the spindle will produce a restraining torque which opposes the disc rotation. When the current exceeds the pickup current, when the current seen by the relay coil exceeds the pickup current, the operating torque on the disc exceeds the spring force and the disc rotates in this direction. When the disc rotates in this direction, so this piece of iron called moving contact, which is attached to the spindle of the disc, also travels along with the disc and shorts or bridges these contacts. These contacts are nothing but the trip circuit contacts. So if these two contacts are bridged by this moving contact, trip circuit gets energized and the circuit breaker will act. So whenever the operating torque exceeds the restraining torque, in other words, whenever the relay coil current exceeds the pickup current, the disc starts rotating and it travels an angular path and closes these trip contacts. Then how to adjust the time setting? So let us take one more case here. Here this moving contact is traveling from this position A. Let us suppose this is A, this is position B, and this position A, it is called the initial position of the moving contact. Here if you see, same contacts are here, and here the moving contact is present here. This is called the moving contact. Here position A dash and B dash. Here when the operating torque on the disc exceeds the restraining torque produced by this spring, this moving contact has to travel this path to close the trip circuit. If you observe both the cases, the distance the moving contact is traveling here is more when compared to the distance traveled here. in both the cases, if you compare both the cases, relay takes lesser time to operate in this case when compared to this case. Here the distance between moving contact A and the trip contacts B is shorter when compared to this case. So we can adjust the time of operation of the relay by changing the distance traveled by the moving contact to close the trip circuit. So here the initial position of the moving contact from where which it starts to close the trip contacts is longer. Here it is shorter. How this position of the initial position of the moving contact can be adjusted? Let me tell you how to adjust the initial position of the moving contact. On the electromagnetic relay, there is something called time setting dial, which is attached to the spindle of the relay. So this is the spindle. So the spindle also rotates along with the disc. Whenever the disc moves in this direction, spindle also rotates. Okay. And to the spindle, there is something called time setting dial. Okay. So this time setting dial, what it facilitates is, it decides the initial position of this moving contact. So there is some time setting dial here also, but I'm not showing it. So that decides the initial position of the moving contact. By using this time setting dial, user can adjust the moving contact initial position. So this time setting dial is external to the relay. It is accessible. So these parts are inside the relay, and this time setting dial is accessible to the user to adjust the initial position of the moving contact. So on this time setting dial, there is a scale, and that scale is called as time multiplier setting. So this in short called as TMS. So this scale ranges from 0.1 to 1. So depending upon the position of the scale, the moving contact position will be decided. If I'm going to next page, see, if the TMS value is 1, if the time setting dial is adjusted to make the TMS 1, the relay takes highest time to operate. But if TMS is equal to 0.1, in this case, relay takes lowest time to operate. Here, an user will adjust the TMS by changing the time setting dial, by rotating the time setting dial. In this case, what is happening internally is, when the time setting multiplier is kept at its lowest position, the distance between the moving contact and the trip circuits and the trip contacts is very, very less, or at its minimum position. When the TMS is made to 1, the relay will take the highest time to operate. In this case, the distance between the moving contact and the trip circuit is maximum. So the user, as per his need, can adjust the operating time of the relay by adjusting the TMS anywhere between 1 and 0.1. So by using TMS, we can find out the actual operating time of the relay. Operating time of relay. So it is given by this formula. Operating time of the relay equal to TMS multiplied by operating time at TMS equal to 1. Okay, I will take a small example here. So let us take the TMS value is 0.5. This is the current TMS value setting. Okay, and we also should know the operating time when TMS equal to 1. So this is this can be calculated by using a stop clock. See, operating time at TMS equal to 1. So this is something, let us suppose this is some 10 seconds. So whenever that relay TMS is set for 1, the relay is taking 10 seconds. Now the TMS is set to 0.5. Then what is the time of operation? T, let us call it as T. So time of operation equal to TMS. The current TMS is 0.5 and the operating time at TMS equal to 1 is given as 10 seconds. So that will give you 0.5 seconds. So you can adjust this TMS value from between 1 and 0.1 and you can obtain different operating times for a same relay. So that is what how we can change the operating time of the relay. Now let us focus on why to change the operating time of the relay. Like for us to understand why the operating time has to be changed, let me take an example of a distribution feeder. Okay, so this is the substation or source. Okay, so we have loads connected here. Okay, these are the bus bars and I'm naming each bus bar, and for each section we have a relay which is intended to protect this section. So these are the relays. So let me name them as R1, R2, R3, R4. Okay. So relay R4 is intended to operate for a fault between D and E. Relay R3 should operate if there is a fault between C and D. Relay R2 should operate for a fault between B and C. And relay R1 should operate for a fault between A and B. All these relays R1 to R4 are overcurrent relays that we are studying right now. Okay. So such kind of operation, that is when the fault occurs in this section, the corresponding relay should operate. Okay, such kind of operation is decided. So that is called coordination of relays. In the sense, the relay will only operate when there is a fault within its section. So section D and E, if there is a fault between section D and D, relay R4 will operate. Okay, let us take this case. Let us take this case. Let us suppose there is a fault here. Okay, when there is a fault here, the fault current flows in this direction. So this is a radial feeder. So it is having only source at one end and the current is flowing in this end. So there are loads connected here. So there are no generating sources here. So current will only flow in this direction. Current is being fed into the fault. If you see here, relay R1, R2, R3 and R4, all these 4 relays are experiencing or witnessing the fault current. Since all these 4 relays are witnessing the fault current, their pickup current, their relay coil current will be greater than their pickup current. As per definition, an overcurrent relay has to operate whenever the current seen by the relay coil exceeds the pickup current. So R1, R2, R3 and R4 will try to operate. Will try to operate in the sense they will try to close the trip contacts. So the disk will start rotating. The disk of these relays will start, all the R1 to R4, all the relays will disk of these relays will start rotating in this direction. But we only want R4 to operate when there is a fault here. Let us suppose instead of R4, if R2 will operate, the corresponding circuit breaker here will isolate, will open. See, let us suppose there is a circuit breaker corresponding to R2 will open its contacts. When there is an opening here, this fault current will not flow. So the fault is isolated. But if you see here, R4 has to operate, but R2 has operated. So what is the problem here? Here the problem is that since R2 has operated, this whole part is getting isolated. Okay, but if you take only R4 is operating, what is the advantage we are having is, see, so this is a substation. So here A, B, C, D and E. Okay. So R1, R2, R3 and R4, right? So there is a fault here. Now R2 has operated. There is an opening here. If R4 is operating for this fault, only this section gets isolated. So there will be an opening here, and the fault current ceases to flow because there is an opening. There is an opening by the corresponding circuit breaker of R4. I'm not showing circuit breaker in the line for simplicity. So the fault current will cease to flow. Now R1, R2 and R3 will reset to their initial position. They are trying to operate. All the 4 relays are trying to operate, but R4 has opened the circuit, and R1, R2, R3 will reset to their initial position. Now, normal current can be fed to the loads connected to those bus bars, right? Because isolation happened here, not here. Instead of R4, if R2 has operated, this whole section gets isolated, and these loads will not be fed. That is a problem. For a fault between D and D, only R4 has to operate, not R2. So this kind of concept is called coordination of relays or relay coordination, or in other words, it may be called as selectivity also. So this relay is able to selectively operate when there is a fault in its zone. It is not. It should not operate for a fault in beyond its reach or beyond its region. So how to bring coordination among these relays? So to bring coordination among relays, we need to adjust the operating time of relays R1 and to R4 to bring coordination among them. So let me take a fresh page and explain that. So here we have R1, R2, R3, R4. Right? So this is the source station, substation. We have loads here. We have loads connected here. So fault has occurred here. So fault is going in this direction to this one. So what we will do is, we will put the operating time here as 0.2 seconds, here as 0.4, here as 0.6, and here as 0.8. So the operating time of this relays will be adjusted such that the relays closer towards the source will have a higher operating time when compared to the relays far away from the source. Now what happens is that if there is a fault, let me name the bus A, B, C, D and E. So if there is a fault between D and E, this relay R4, R1, R2, R3, R4, all these 4 relays will try to operate. So R1 to R4 all will try to operate because fault current is being seen by all the relays. But R4 is having the lowest operating time. It is set with its TMS is set such that its operating time will be 0.2 seconds. So R4 will close the trip circuit at 0.2 seconds, and the circuit breaker will open here. Okay, if the circuit breaker will open here, this fault will be fault current will no longer be fed into the fault. When there is no fault current, all these other relays will go back to their initial position. The disk will go back to their initial position, or the relay will reset to its initial position. So if you see here, the desired coordination is obtained by setting different operating times to different relays. If there is a fault, if relay R4 is not able to clear the fault at 0.2 seconds, let us suppose there is some problem with relay R4, and there is some malfunction in R4, and it is not able to clear the fault at 0.2. So if after 0.2 seconds, also if the fault current is being flown because of malfunction of R4, then R3 will isolate the fault, or R3 will operate at 0.4 seconds. Okay, so if R4 will fail to operate at its operating time, then R3 will operate. Okay, so here R3 is called as backup relay for R4. So if R4 will fail for any reason at 0.2 seconds, if it is not able to clear the fault, or if it is not able to close the trip contacts, the fault current will persist to flow, and at 0.4 seconds, relay R3 will operate. Same case, if there is a fault here, R3 should operate at 0.4 seconds. If it doesn't operate, R2 will operate at 0.6 seconds and it will isolate the fault. Okay, so in this zone D and E, R4 is the primary relay. So in between D and E, R4 is the primary relay, primary relay, and the backup relay for R4 is R3. Here to achieve coordination among relays, we are intentionally making the relays to operate at different operating times. So here the operating time of this relay is relay R1 is 0.8 seconds. In the sense, if there is a fault here, this relay R1 will take 0.8 seconds to operate. Okay, so this is not having any coordination responsibility. Here R4 is having the coordination responsibility. If you see that R4 has to isolate for a fault present here. Okay, so for this relay there is no relay in its upstream. So it will be set with 0.8 highest operating time, 0.8 seconds. So why time setting is necessary? Because to achieve coordination among group of overcurrent relays. So that is pretty much about how time setting is being done in overcurrent relays and why it is necessary. Please subscribe to EasyBTech channel and keep following the power system protection playlist for more videos on these topics. Thank you.